My name is Val Kessler. I am the product manager for Dwyer, overseeing the level and flow portfolio. So just to provide a brief overview of what I'm going to highlight, I want to first just go through and just discuss the type of flow meter that this is specific to. There's a lot of different types of technologies and flow meters. We want to make sure that we specify that this is for insertion flow meter technologies. And then I'm going to go into 4 major sources of errors and their effects, and then discuss solutions that we came up with in order to overcome those errors, particularly with our Series IEF insertion electromagnetic flow meter. The 4 sources of error that I'm going to highlight are going to be aware of moving parts. They're unique to paddle wheel or turbine type of flow meters. Then talk about how variations in pipe size can actually affect your flow reading. Then I'm also going to highlight a little more about installation depth and the importance on the correct installation depth for your accuracy of your flow reading. And then finally highlight how fluid composition actually affects your readings as well. So just to start off, there's a lot of options when it comes to fluid flow measurement. It can vary from different technologies as well as installation configurations. The technologies can range from differential pressure to paddle wheel, as I mentioned, turbine, electromagnetic, ultrasonic, just to name a few. However, there's also differences in the installation configuration. The most common installation configuration you tend to see are what is considered more of an inline type flow meter. An inline type flow meter typically is attached to a pipe and is connected inline in your flow piping system. Another popular installation configuration is insertion, which is what I'm going to discuss in the next few slides. And in that type of flow meter, that's actually inserted into your pipe application. There's some benefits associated with that. And another being a clamp-on type configuration that allows you to actually clamp on the sensors onto the pipe itself. When looking at these type of flow meter configurations, we're really kind of focusing and talking about HVAC applications for such as monitoring boiler feed water, as well as chiller or condenser loop water monitoring. And the reason I bring this up is because in these applications, having the ability to hot tap or to pressure tap is extremely important. Particularly with a hot tap application, you're able to utilize an isolation valve to allow you to actually install and remove the flow meter without having to actually cut down your system or drain your system of glycol. And it really allows you to not only do retrofit applications where the system itself is running with the install, but it allows you to remove the unit in the event that you needed to do any maintenance or any calibration of the flow meter as well. So insertion type flow meters really inherent well for that, because you can utilize them with those isolation valves and allow you to easily and seamlessly remove the product without really disturbing your flow. So there's a lot of costs associated with having to actually turn down the system, so being able to have that is definitely a big plus. So in addition to insertion types, the most common, particularly in these type of applications, what we tend to see are mechanical type of insertion flow meters. They're really kind of what we've seen to be more of the market standard. So they can vary from paddle wheel to turbine, and they really function and they depend on the constant movement of a rotor, an impeller, or a turbine in order to actually get you the velocity and therefore the flow of your application. The issue that tends to come with mechanical type flow meters is that they tend to get, and they are susceptible to long-term wear. What tends to happen is the bearings themselves, which hold the shaft in place, can actually create a gap in between those, which then will cause actual movement in the shaft itself. That shaft in turn will cause the motor, the impeller, the turbine to move, and that will not only affect your accuracy, but long-term can lead to the rotor, the impeller itself to break or to fall off altogether. So the obvious solution to trying to avoid any kind of wear of moving parts is a non-moving part technology, which is what we went ahead and moved forward in introducing with an insertion mag meter. With an insertion mag meter, it features electromagnetic technology where there's no moving parts to wear or to break. You really just have a sensor that's located into the flow with electrodes that utilize applied current and voltage to give you your actual reading. We also find that internal pipe diameter can actually be a large source of error when it comes to flow measurement. And the reason for that, when you have an insertion flow meter, you really depend on the cross-sectional area to take the velocity to give yourself your flow measurement. And if you just look at the nominal pipe sizes and the tolerance ranges allowable for both the external diameter and the pipe wall tolerances, you can actually stack up to a fairly significant amount of error. So again, since the error in the flow is an equation of the inside diameter square, you can actually see on this graph that I have depicted here that you can go from a 2-inch pipe size can have as high as a 10% flow error, and a 12-inch, so obviously it's a little more exaggerated on the low end, up to 4% in a 12-inch pipe. So that could be very surmountable when you're looking at trying to maintain your accuracy in your flow system. So what's a good solution for that? A good solution for pipe diameter variation is to ensure that you have your actual circumference of your pipe in your application as well as your pipe wall thickness. So what we're currently offering with our insertion mag meter is the ability to have an ultrasonic thickness gauge to actually measure the thickness of the pipe wall, in addition to taking a measuring tape to get your circumference of your pipe, of your actual application, and be able to put that information into a very easy to use intuitive display, and that unit itself will compute the actual pipe inner diameter, which is a function of the wall thickness, and the outer diameter, and therefore calculate the actual area of your application, reducing those errors that we just saw in the previous slide, and therefore yielding a more accurate flow reading. Now you'll kind of see this also play an effect in the next source of error, which is the installation depth, but it's extremely imperative for insertion flow meters that their actual insertion depth is where it needs to be. Particularly, it needs to be placed at where the calibrated velocity point was when the unit was actually manufactured. So in order to do that, you have to keep in mind that an error, you can actually get errors of 0.5% of reading. You have to make sure that your insertion depth is close to 0.05 of an inch. That's in order to ensure that you're getting less than 0.5% of reading error on your flow meter. So if you remember when we discussed the NPS tolerances, or the National Pipe Standard tolerances in the pipes, you can actually, in an 8-inch carbon steel pipe, it can vary in and of the tolerance level of that 0.05 of an inch. So it's extremely important that you understand what the actual insertion depth is, but in order to do that, you need to also understand what the true inner diameter of your pipe is. So as I can see, is that you can actually see here on the graph, what I have depicted is the percent error of probe depth on a Schedule 40 carbon steel. And what you're looking at right here is that for this 8-inch carbon steel, the correct insertion depth is a little past halfway point, which would be around this 4.8 of an inch here, 4.8 inches. So you can see that a variance of as much as half of an inch can actually cause a 5% accuracy percent of flow error in your actual reading. So that was fairly surprising. So what is really a good solution for that? So if you do in fact have variances in your inner pipe diameter, really having a tool to promote what that actual depth alignment is essential. And also going back to being able to input that information in the display is actually not only able to determine what your correct inner pipe diameter is to give you the correct flow rate, but it can actually go through and provide you the actual precise depth for the circumference in the pipe wall to ensure that you're getting that correct accuracy on your actual insertion as well. So this ultimately allows the probe to set at the optimum length very easily with the use of the tool that I have displayed here, as well as the display where you would be able to go through and put in that information. The last source of error I'd like to discuss is fluid composition. This is common in other flow meter types as well, but particularly in HVAC type of applications, again, boiler, chiller, loop applications, glycol can be added to actually lower the freezing point for the cooling systems. Typical concentrations can actually vary from 25 to 50%. But what happens is this variance causes a variance in the viscosity as well as the density, and that will ultimately affect the flow profile around the insertion flow meter. So in particular for an insertion mag meter, the errors can be greatest at lower velocities and they can change with temperature. And as I show here actually on this chart, you can take a look and see that from 25 to 50% you can have as much as an additional 5.5% error in the flow, down to, with a 25% glycol input, about 3.5%. So how can you modify and how can you ensure to avoid that error in the fluid composition change? Compensate for changes in the viscosity, density, and the water and glycol over temperature and velocity. Fairly simple. So what we've been able to actually do with the display of this flow meter is put in the corrective curves within the display to actually allow for correction of the percent glycol through the flow temperature. In addition, we have a temperature sensor located in the probe of the unit that can compensate for that as well. So as I mentioned, there was quite a few flow errors associated to flow technology. I wanted to really hit on the four major ones that we focused. And by being able to offer a non-mechanical flow meter with precise depth installation via the display, you're really able to make a lot of corrections as far as the flow is concerned to ensure that you're getting your most accurate reading.